Good evening. My name is Ridwan Chaudhary, and welcome to my presentation about the first stainless steel vehicular bridge in Europe. Let's get to it. All right, so we'll start off with an introduction. So when I first set out and looking for projects to research for this project, I was actually pulled towards bridges. And this is mainly because our CIVL 4000 project is actually a highway bridge over Credit Valley River. It's actually a reinforced concrete box girder bridge. Although our specialization this semester wasn't in structural, I thought it'd be interesting to learn a bit about a road bridge that utilized steel instead, and possibly use that knowledge for capstone, maybe as well. So let's start with a little history of bridge materials, get some historical context. So the earliest bridges actually were made of wood. Following that, began the use of stone and low-quality concrete. Iron wasn't used as the primary bridge support until 1741 in England. Steel eventually actually became a common material in bridges in the late 1800s. In 1912, an English metallurgist named Harry Brearley was actually looking for a corrosion-resistant solution for gun barrels, I guess very likely for wartime. So long story short, the start of the industrialization of stainless steel was around early 1900s. And it didn't take long for stainless steel to be caught on the radar of recognized by prominent engineers. So now that we have some historical context, let's move on to the project of concern. So we'll start with some background. So this steel bridge was built on the rocky coast of Menorca, Spain. Menorca is actually a Mediterranean island. It spans 55 meters over the Algandar Creek, and it opened actually in 2005. Cala Galdana is one of the most beautiful beaches around these islands, so that's the name of the bridge itself. So why was this bridge even needed? Why was this project even conceived? Well, it was needed to replace the previous bridge before it, which was made of reinforced concrete, which had become corroded due to the marine, saltwater, and coastal environment. Basically, it had lasted 30 years until finally being decided by the owners in 2003 that it was time for it to go. Yeah, that's pretty much a little background on the bridge itself. So let's go into conception. So in terms of conception and architectural design, in 2003, the owner had 4 key requirements for the architects and engineers at Fidelta. And Fidelta is the firm responsible for the bridge, the design, as well as architecture, and they were based in Barcelona, Spain. So the 4 requirements that they had were that it had to be environmentally friendly, it needed high durability, so a long service life, it required minimum maintenance, so lower maintenance costs, and it had to be a symbol of innovation as well. And the width of the mouth of the creek, which the bridge had to cross over, was around 40 meters, so another constraint or minimum requirement there. Tourism revenue is also very important in this area. So a material which blends in with the natural surroundings and causes minimal disruption. Twin construction was heavily required and desired. This eventually prompted the choice of stainless steel by the architectural and engineering firm responsible, but we'll get to that in the next slide. So material selection. Due to these different requirements and objectives, different grades of carbon steel and stainless steel were considered. And these were considered rather than concrete, according to the previous issue with the previous bridge. This was also to appease the innovation request, so as to have the first steel road bridge in Europe, which is a pretty big feat in itself. The table in the slide you can see in the top right was taken from a European standard, and it shows the grades considered when trying to select the material. The duplex grade 1.4462, you can see that in the 3rd row of the table. It was eventually selected because of its high strength, exceeding most regular steels, because of its high ductility and durability in marine environments, resisting corrosion from chlorides, as we learned in class. Post-construction quality control tests were carried out to make sure everything was fine, and they exceeded expectations for the material. Another point to note is that stainless steel is 100% recyclable, and a large percent of it is made via recycled materials. So this also appeased the environmentally friendly request as well. Well, let's get further into the engineering part a bit more. The governing codes used was a Spanish code for design of steel bridges. This was key for making recommendations in regards to compliance and obviously the verification of resistance at the ultimate limit state, ULS, and the serviceability limit state, SLS. The other codes or standards used were similar to the steel handbook that we've studied throughout this course. Even comparing their table of contents, there was a lot of overlap. That would be expected, of course. Some of these design manuals include the Eurocode Part 1 to 4, design of steel structures, as well as manuals for stainless steel specifically. Moving on, let's get right into the design. So the bridge covers 40 meters width of the creek, so with a 55 meter total length, but the main span of the bridge is about 45 meters. The deck is 13 meters wide. It encompasses 2 lanes of traffic and 2 pedestrian walkways, separated by a low concrete wall and arches, as you can see in the image in the top right. It'll help you visualize it. If the roadway is constructed completely above the arch, we can refer to the bridge as a true arch or a deck arc. This is when the road is above the deck, and the arch is above the deck. And when it's below the deck, that's when it's called a through arch. But in this case, the arch is below as well as above, so we call it a half through. According to the Spanish code, the typical ratio of rise to span for a steel arc bridge is in range from 1 to 5 to 1 to 6, because if the arch is too flat, the secondary bending effects can become extremely large and result in a pretty uneconomical design. Bearings were fitted into the base of the abutments, and they transmit the horizontal forces into inclined stainless steel struts rather than into the foundations. So the arches are joined to 2 longitudinal beams spanning the full length of the bridge. The bridge behaves like a self-anchored arch in this way, and that's helpful because you don't need ties then. Longitudinal beams support transverse beams as well. You can see in the picture in the bottom right. And those carry the bridge deck. Composite action between the deck and the transverse beams is achieved by shear connectors. And those are welded along the transverse beams. What else there's? So these images on the right are very helpful in seeing how the beams are underneath, and the arches underneath the bridge as well as on top of the bridge. And you can see how the longitudinal beam carries the transverse beams, which then carries the bridge deck as well. So it's a very helpful image right over there. All right, if we continue on, we can see that the arches have a triangular cross section with a central web and a depth of 700 millimeters. In the central zone of the bridge, the arches actually rise above the longitudinal beams, and throughout the zone there's a cellular steel plate connected vertically between the two, so that the cross section is almost kind of like a hybrid I-beam structure. You can see in the picture in the bottom right. This allows direct transfer of the vertical loads in the longitudinal beams into the arc. The transverse beams are 2 meter spacing, yes, and the rectangular hollow sections 250 millimeters wide. They have variable depth from 500 to 570 millimeters, and this actually enables the deck to have a cross slope, which is important because the wearing surface needs a cross slope for drainage purposes. When rainfall falls onto the road, you don't want it to be stuck in depression storages. You want it to fall to the side where the drainage can lead it to the stormwater pipes or whatever drainage system is on site. The thickness of the beam sections vary between 10 to 12 millimeters, and are connected to the longitudinal beams beneath and to the concrete deck above as well. And they're connected by 20 millimeter diameter steel shear connectors. Yeah, that's about it for this slide. There's a side profile of the bridge, which is quite helpful. And well, almost done. So, of course, using all these parameters that I mentioned, the steel members, they were decided based on loading cases, the worst loading case. But first, you'd have to estimate the AADT values, annual average daily traffic values, also the DHV, the design hourly volumes, to get like kind of an idea to estimate how much traffic there'll be, so you know how much load to expect. As we know, an arc is actually very efficient in resisting uniformly distributed loads over its entire span. However, concentrated loads, it's a bit different. For partial span loadings, can be flexible and develop large bending stresses. So loading scenarios for the bridge can be seen in the top right. There's full loading, half loading, and there's also full and half loading in the other directions as well. The worst loading scenario for a bridge would have to be when the max loading for half of the longitudinal span, so case B. With a few preliminary calcs and manual calculations, you can simplify. I'm actually simplifying this quite a bit, but you can just see it, just to see the comparison. For the full loading, the max deflection would occur at L over 2, with the max moment equation approximately being WL squared over 8. Whereas with half loading, you can see that the max deflection would occur at L over 4. So that makes the equation for max moment now WL squared over 32. So in that case, you can also split it up into two superimposed loads, one full loading and one with just half. So as you can see in the image in the bottom left, kind of the superposition of that scenario. So yes, you design for that worst case scenario, which would be half loading of the bridge. And construction to end off the last aspect. Construction actually began in October 2004, starting with the demolition of the existing bridge. The welding processes used, as we learned in class, some of them were SMAW inert gas, covered electrodes, MIG, FCAW, and SAW without preheating and not exceeding 150 degrees Celsius between two consecutive passes. As you can see on the slide, after welding, all weld areas were pickled. Pickling is a process where we can apply pickling paste to prevent oxidation or remove surface contaminants as well, created during welding. So this is very helpful, and it's also encouraging to the formation of the passive layer, and this prevents corrosion, as we learned in class. The main stainless steel structure was assembled on site from 8 sections. Each section was lifted on temporary supports. This facilitated welding, and all welding was controlled using standard methods of visual inspection, X-ray, magnetic particles, etc. The final cost, was 2.6 million euros, completed in June 2005. So from conception to end of construction is about 2 years, 2-year project. And we're finished. These are some of the references I used to gather my information and research the 4 themes or aspects for the aspects of this presentation. And thank you very much for listening. I appreciate it. And I found this steel structure quite fascinating, and I hope you did too. And I hope I was able to make this presentation interesting and the structure interesting for you. Thanks a lot. Bye.